Announcement. Yes, everyone has seen this now. All read it. Can I erase it now?
Yeah.
Okay. CST 19 team signups for next two assignments are due on Tuesday, and I can't erase it.
There's an eraser on this side.
Other side. Okay, so back to reactors, right? You remember what we did last class? Okay. So I get my reactor, I can write little programs, and the idea here, of course, was to get them to reflect and update the state of the world. I want to talk about two more examples along those lines, and then talk about something else more high level, and then we can maybe take some questions. So you remember the central idea here is there is some notion of the state of the world, the state or the model. And what we have is we have update functions, consume and produce these. Then we have draw functions, right? And what other kinds of things have we seen? What other parts of reactors have we seen? So the controller is built into the reactor, right? So that's definitely, there's a controller making the whole thing work. What else? Other parts?
Ticket.
Sorry?
Ticket.
Yeah, so tickers is the updates, right? Those are the things that are changing on tick. Yep.
We also saw stop conditions.
Stopping conditions. So stopping conditions basically are like don't go anywhere else. Yeah.
Input from the keyboard.
Yeah, so we also saw that there are multiple ways to cause new worlds, right? So it could be a tick, it could be a key. You could imagine, can you imagine other stimuli? What other stimuli can you imagine?
Nice.
You can imagine mice, what else? I mentioned some others in class actually. Tilting and network packets and various other things, right? So it's a function of what services you want to provide on your platform and what your platform even provides. Like like this thing doesn't have a tilt on it, but some other devices do. But there's a standard way of thinking about all of these. Yeah.
The initial state.
Yeah, the initial state, right? Like how do we even start the whole machine going? Yeah, the hand
That was the
same thing.
that was
Okay,
the key.
good. Okay, so that's what we've seen so far. And what I want to do is actually let me. You know what? Before I do that, let me do another example. So I wrote a little bit of code last night. Okay, so you can't read the program. That's okay. So I could run it, and right. Okay, so the question is, I was purposely small. What is the state of the world in that program? So what I'd like you to do is I'd like you to conduct a little in-class exercise, talk to your neighbors. I assume I assume many of you are familiar with the game called Pong, but if you're not, you saw Pong, okay? So what I want you to do is talk to your neighbors and come back and tell me what the data structures are that are going to represent a world in Pong. Go.
Position of what handles, I don't know if maybe if you want to score I mean, you could put it in.
Talk to your neighbors, come on. Talk. You already have 30 seconds.
Speed is Most recently, so just I think we got if
How many of you need more time? How many of you need more time? Okay, in 5, 4, 3, 2, 1, and we're back. Okay, let's see if we can get the accumulated wisdom of the class. All right, I have no idea how we're going to merge all of your answers. Well, what the heck? Let's try. Okay, who wants to start off? How about we start with some group? How about back there? Back there. What do you folks have?
We had a simple position for both the right and left paddles.
Okay, so position for L paddle, a position for the R paddle. Okay.
And we needed to know more about the function of how the ball was moving.
Well, so let's take the simplest interpretation, just what we saw on the screen.
So then position, speed, and direction.
Position for ball, speed for ball, direction for ball. Yeah? Is that everything? Okay, next group, who's like, let's go here, yeah.
Yeah, so for us, instead of speed and direction, we had delta x and delta y for ball.
Yeah, so you could imagine combining these two, right? Okay, next.
We thought about possibly expanding it by having sort of a list of paddles or a list of balls to make it more sense. As like a
Yeah, it's Pong, it's got two paddles. What is a list of paddles in Pong? Yeah, I suppose. I mean, you need a list of controllers or something. Yeah, okay. I mean, not perfectly, totally legit. Yeah. Okay. Next.
So we did a vector for speed and direction, like they were saying, and then also you only need. I assume Posen is XY pair.
Yeah. So what's Posen? Posen is probably going to be an XY thing. Yeah.
So you only need one number for the paddle because.
Okay. So you had instead you had a number for and a number here. Okay. Next. Yeah.
So our paddle also had a position, not just a number, and we had velocity for the ball rather than speed.
Okay. Velocity and stuff. Okay. Good. Next.
You can add a scorekeeper function.
Oh, score! Haha, okay. Yeah, score. I mean, what's the fun of Pong if you're not like getting scores? Okay, yeah.
You need like a background, a black background.
A black background, is that part of the world?
It's not part of the world. But
Okay, so we're just focused on, yeah, so there's graphical elements, right? Absolutely, there's graphical elements, like how do you draw the very sophisticated paddle drawing, right? Which at least in my code is like a big giant rectangle. Or the very sophisticated ball, which is a square, yeah. So yes, you need all the graphical elements, absolutely, yeah.
Something to prevent the ball from like going out.
Yeah, so now we're stepping outside the world model, right? Like, what's the essence of the state of the program, right? So, does anyone have anything else they want to add to the state of the program? Yes.
If speed is dependent on time, then we should have some kind of indicator.
So if speed is dependent on time, Pong pretty unsophisticated, but you could imagine time being a function of some of these things. Yeah.
Oh, I feel like you don't necessarily need like a number for the left paddle if it's just a function like based off where the ball's at. You might not need to store that information.
You may not need to store. Okay, great, good. Finally, we have a dispute. Okay, like let's just consider this. this vector is just another way of saying speed and direction, right? So both of these are legitimate, and you know, if you like your physics, you might like to say vector. If you don't like your physics, you might say speed and direction. But these are essentially the same thing. Okay? There's a little bit of a dispute here about number versus position. And now there's a bigger dispute of whether we need these at all. Okay? So let's resolve the more important one, right? There's no point disputing this if we don't need either of these. Any other disagreements on the board? Yes?
I don't know if we need speed because like it might just
I'm sorry,
be
which speed? This
it
speed
might
here?
just be a constant speed for the ball.
Okay, so if we keep speed and direction separate, then the question is this like a constant or not, right? Okay. And if we record as a vector, then we can't split those apart, so it doesn't really matter. Yeah. Okay. So let's get this one out of the way, right? I mean, so in Pong, it is actually a constant in traditional Pong. So you can think of it as a constant, but if you just represent it as a vector like I did in my code, then the issue just sort of dissolves away. Because if you have delta x, delta y, then you're just recording that anyway. Okay. This is the more interesting dispute here. Do we even need to record this? Talk to your neighbors. I want to come back with a yes/no vote. Go. Five, 4, 3, 2, 1. We're back. Okay, so we're going to do a voice vote. So how many of you think we do need to keep these, whether they're numbers or positions is to be disputed? How many think we do need these? How many think you don't need these? As Mahatma Gandhi said, in matters of truth, a majority of one suffices. So, to be brave, it's okay. Yeah?
Sorry, just clarifying the question, like, is it like a single player game? Is it one paddle like...
Oh yeah, that's a good question. We do, nobody asked. Okay. Well, so presumably it's a two-player game.
Okay.
Classical Pong is two-player,
Okay.
right? Okay. So, if it's a single player, what does that affect? Okay, so our goal is not to spend a whole lecture on Pong, but this is the kind of modeling you might want to conduct. Notice one of the things that we're doing here, we're able to have all of this discussion just at the level of data structures. Right? We're not talking about visuals, we're not talking about anything else. We have these images in our head, of course, but we're able to have this conversation simply at the level of data structures. And that's actually quite a powerful thing, because data structures are relatively easy to talk about, right? And by defining the data type for our game, we get to record, like in the act of writing the data type, we get to have all these disputes. If you are part of a team building something, you get a simple thing around which to coalesce the design discussions. Because there is actually an important point here, right? This addition of time here, that actually changed the game. Because the question is the velocity of the ball constant or not? If the velocity of the ball is dependent on other things, what might it depend on? And in particular, if it depends on, essentially, what does time let you do? It lets you basically say that the ball moves faster and faster, right? And eventually, one of the players can't keep up with the ball and they lose. It actually sort of guarantees that eventually the game is going to terminate, right? So that is an argument you can have, and talking about the model lets you have this discussion about whether time belongs or not. Okay? So it gives you a point at which to crystallize the design discussion. And then once you've captured it in the data type, you can also write examples that demonstrate what you intend the game to do. And all of this is before you've gotten to the graphics part. And I'm not putting down the graphics part. Right? It's really hard and interesting, and we have people who do that for a living and do it quite well. So it's not to put it down, but it just says that there are multiple skills involved in the act of designing a game. And there's one way in which you can capture this that is independent of the graphics. And as I get to talk sometimes indirectly to people at, there's a game studio called Naughty Dog. Anyone heard of Naughty Dog? Okay, Naughty Dog are pretty hardcore racket users, so I get to talk to them. And so what Naughty Dog does is they basically split tasks up between different languages. They use Racket to build a collection of different programming languages so that different people with different skills can express their part of the game design just using that set of skills. Right? So they get different language for each part of the game design process. So this is a thing that's important then. You want to have people who are expert at thinking through the problem, experts at drawing, experts at data structure design, and each of them use different languages to express their ideas. Okay? So that's one of the ideas I wanted to point out that you get out of thinking about designing systems this way. Okay? So what did I have actually? I had a position, a vector, and two numbers. I chose numbers because you don't need the whole position of the paddle because the paddles only move in one dimension. You could have a position, you can choose not to. Okay? All right, and the details aren't really, it's just like a whole bunch of, usual stuff, right? Paddles and movement and reflections and boundaries and stuff. Okay, so now I want to move on to another program. Where is this? Yeah. Okay, so this is a much, much, much simpler program. I'll give you a minute to read it and tell me after a minute, I'm going to ask you what this program does. Okay, talk to your neighbors and give me a quick summary of what it does. Go. All right, in 5, 4, 3, 2, 1, we're back. Okay, this wasn't meant to be horribly complicated. There's no trick here, except there is one thing that you should find annoying about this program. So, first of all, can anyone predict if I run this reactor, what's going to happen? Run meaning interact. I don't think nothing will happen. Like many of you were drawing the answer and yeah, come on, use your hands, animate with your hands. Yeah, there you go. All right, okay, good. Okay, so if I do this, good. Okay, excellent. All right. Yes. That was an intermediate step in the design of the Japanese flag, perhaps, or something. Okay, why should you be annoyed at my code? Something about my code should annoy you. I mean, it's the behavior, just so you know. You don't know this, but that's actually the behavior I wanted to see. So obviously it's a correct program, but there's something actually, there should be dissatisfying about it. Yeah. we never use delta t, okay, so that's definitely a problem, right? You got random constants floating around for no good reason, or perhaps I do have good reasons, okay? Why else should you be annoyed? Something about my code is annoying, yeah.
You're kind of mislabeling some stuff.
I am mislabeling some stuff. That is a strong accusation, sir. Yes. What am I mislabeling?
Okay, so your parameter.
Pay attention to this. This is really important.
The parameter that you care about is time.
The parameter that I care about is time, and I actually say x at t. Given the t, you're going to tell me what the x is. Yes?
But your initial state.
But my initial state is init
labeled as x.
x. Right? It really ought to be init t. Now it happens to be that init t is also going to be 0. Time usually starts at 0 in programs. Okay? But really that should be init t. And similarly, my onTick is really updating what? It's not updating the x position, right? It's updating the t position.
You should update it with delta t.
Yeah, so I could imagine, yeah, so you can imagine a delta t, whatever, right? Okay, so there's a few different things here that are purposely mislabeled. And so what's really going, yeah?
You're also like not representing the world state you care about.
Oh, hold on to that, hold on to that, hold on to that, hold on to that. Okay? Okay, so let's just, I think I got everything now. Okay, yeah, good. Okay, so now we have a more honest representation. Okay? But what is the state of our world? It's what?
Just the circle. You don't care about the rectangle, right?
Yeah, no, we don't. But what's the actual state of my world? In my reactor, what is the state of my world? It's even simpler than the circle. It is just what? Time. Time. Is that really, is time capture the essence of what we're trying to do here? I mean, every program in some sense has some notion of time. This is completely uninteresting, right? So I would argue that this is actually not a very good model. It's actually, let's be honest, it's a bad model. It doesn't tell us anything about the system. Imagine that instead my ball were traveling more like a sun-shaped thing. Okay, so it's actually going to, and some sort of parabolic motion or something like that, right? Would my state look any different? No. Where would the parabola be represented? Will it be represented in the updating function? No. Where would it be represented? In my drawing function. So I have two completely different notions of motion, right? And the only difference between them is embodied in the drawing function and not in any way in the essence of the problem. Right? That seems dissatisfying. So what should our model really be? What is the actual state of the world? What's the actual state of the world?
The coordinates of the circle.
Yeah, where is the circle, right? So I'm going to now show you a different reactor. Okay. So now what I have is given a state of the world. So now my init x really is an init x. It's where is the sun thing at the starting point in time. And on every tick, I want to compute a new location for it. And in this case, since I happen to have linear motion, I didn't want to turn this into a physics class or like a math class of like, dealing with parabolas and stuff. So I just have linear motion. But if I had a different kind of motion, that would be represented in my next x instead, right? So the show function now has returned to being what it should be, a trivial function. Show's only job is to provide some visual decoration, not to compute the essence of the idea. Does that make sense? Okay, and now if I run this one, I can interact with the diff-r, and it's the same program. Okay, it's still the same program, but now my model actually embodies the interesting part of my program rather than the uninteresting part of the program, which was previously buried in my drawing function, which is not where it belongs at all. Right? So what this says is a reactor can be, you can have the same system represented with different reactors, and some are genuinely better models than other models. And when you build systems, when you build GUI systems, this will become a thing you run into. So you recall I was telling you last class about model view controllers. and I said you might have a model here, and you have some controller code that the controller part's kind of the boring part here. Maybe I represent it as maybe I have a spreadsheet, and maybe I have a pie chart or something like that, right? Now, each of these things has some information that's local to it, right? There's information about which colors I'm using for the different pies, right? The pie slices. That's not model information. That's basically state of the pie chart, right? Which cells am I currently showing on the screen? That is state of the spreadsheet. It's not relevant to the model. But the model really needs to embody the essence of the information that's common to all of these things, right? My first reactor doesn't do that. The actual interesting information is in the view rather than in the model. In my second reactor, I've put all the important information in the model, and my view is just a trivial representation. It's one visualization, and maybe I have different visualizations. Okay? And so when you design systems using Model View Controller, remember to ask, what is the real essence? What belongs in the model? What belongs in the view? Okay? Notice what's not in the model is the fact that I have you were talking, some of you were talking about the colors and the background and stuff like that, right? The fact that I have a circle of a particular size and the fact that it's red against a white background, that's not really part of my model. That's this particular visualization, and a different visualization might pick something different. Does that make sense? Okay. So one last thing I want to point out, like why did I even show you this? So one thing we can do when we construct models like this, and now this relates to something I talked about last class, is we could also test these, right? So I can write a function that says after n ticks, where am I, right? And I now have these two different reactors, right? Now my diff x is basically after n ticks, what happens, what is the state of the reactor? In contrast, my first reactor, there's no point even asking the reactor, where are you? Because the reactor head was just trivial, right? So I'm actually going to call this function, and I'm going to ask, are these the same? Okay. So they looked visually similar, but debugging two visually similar things is hard and subtle, but I can actually programmatically test it and ask, are they still the same? I can ask test after 100 is true, and comes back and says yes, right? And in fact, I could even go further, right? I could basically say, for all of the first 100 values, is it true? And does I, in that range, satisfy the test after function? Right? And it comes back and says yes. And so now I start to build my confidence that in fact I have got two equivalent models. Satisfies familiar? Not familiar? Does anyone need to know what satisfies is? Satisfies? Okay, good, right? So I satisfies test after, it says that test after is true for all of this. Okay? So this is a way that you start to build confidence in systems. You write small tests, you check on small cases. Once you know it's true, then it's only then is it worth trying to prove that the two things are correct, are equivalent. And yes?
This is about the for loop. How do for loops in Pirate work versus other programs?
Oh, because there are no for loops in Pirate. For is just a way of writing higher order functions, that's all. For literally turns into a lambda, so this literally turns into each of lambda I satisfies test after and on range of 0, 100. Okay, so literally this code went over here, this code went over here, this code went over here, and then the lam, the colon, and the end, and the comma, and the parentheses were supplied for you by Pirate. So there is no such thing as a for loop in the language. Yeah. And if we've successfully fooled you until now, that's great. That was the goal. Okay? So, quick comment I want to make. I've actually shown you something kind of interesting about modeling physical systems. There's a reason I call them param and diff. In the diff version, what we're computing is the difference from one state to the next. Right? this is basically a finite difference. So basically we're writing a differential equation as finite differences. Given a state, we're simply telling you how to compute the next state. In contrast, in this version, this x at t doesn't compute differences. It takes a t and tells me the entire state of the world at t. I assume many of you had high school physics. Some of you had high school physics. High school physics, from what I can tell, is the science of things that have closed forms. It's not physics, right? It's all of the things for which I can give you a formula in terms of time t. It's always, given t, tell me what happens at t. And in a way, that was the great achievement of Newton, right? As Newton basically came up with this mechanics that said, given t, I can give you a prediction of what happens at t. And so that's why you do a whole lot of linear motion and quadratic motion and basic acceleration and stuff like that. But there's a whole bunch of physical systems that you cannot model this way. It's either very difficult or provably impossible. So gravitation, of course, Newton's gravitation, right? One of the great intellectual contributions of humans. And it's great if you have two bodies. When you have three bodies, why isn't there a Newton's formula for three bodies instead of two? There's a formula for two. What about the third, fourth, fifth, sixth? Turns out even when you get to three, you can't have a closed form. So that's why you don't do three-body gravitation in high school, because you can't, the way you're taught to do physics in high school. When you get to more bodies, you can only express it in differential form. And there's a lot of other systems that it's really hard or impossible to express in closed forms. So if you take predator-prey models, right? So predator-prey models are standard ecology things. So what are you trying to say? Well, you've got some population and it's always, I don't know, like foxes and rabbits or something like that. Pick your pair of animals that don't get along well, right? So you have a population of foxes and you have a population of rabbits. At time t, you have some population, so many foxes and so many rabbits. What you want to know is what's going to happen over time. And so the way this typically works is you say, well, foxes don't eat every possible rabbit, right? I mean, they eat some number of rabbits, and the number of rabbits that foxes eat is proportional to how many rabbits are even there, because a fox has to find the rabbit, right? The number of rabbits that survive is proportional to the number of foxes, right? So the more foxes, the inversely proportional, right? More foxes, fewer rabbits survive, fewer foxes. And so what happens is, and there's actually, these are pretty interesting models, because if the foxes get too rapacious, well, they do really well, they reproduce really well, because they've got lots of food, and so there are more and more foxes. More foxes means fewer rabbits, because there are more foxes, and then poof, no food source. And no food source means all the foxes die out. So basically both die out. And this is essentially what happens with international fishing. Right? This is more or less what has happened with fishing. You overfish and then everyone's really prosperous. Prosperity means more people say, let's go fish. And the more people that fish, well, there's fewer fish. And then eventually there's no fish and everyone gets really angry. Right? And this is why Cape Cod. Where does Cape Cod get its name from? Because there was cod. There was cod. The fish were teeming. The waters were teeming with cod. There's no cod anymore. You can find great white sharks, it turns out, but not cod anymore in Cape Cod. Okay? Because overfishing, right? And it's a whole story about international overfishing. So basically, it's a predator-prey model where the predators are the human fishers, okay, and the prey are the fish. And if you overfish, you can see that. So that's what a predator-prey model is. It's kind of not very meaningful to talk about a closed form solution. I mean, you can ask, well, given these initial parameters, at time t, what will be the value of the predator and prey? It's really hard to calculate this. But it's really easy to express this as a differential form. So you usually express these as differential equations, where you say, given this size of population at time t, given these numbers, what is going to be the number of predators at t plus 1? What's the number of prey at t plus 1? And it's actually a really simple formula. I basically more or less told you the formula. You just need some coefficients, okay, that tell you what proportion they're going to affect in. And then once you have the coefficients, you run a simulation, and it's pretty easy to figure out what's going on. Let me give you another example of an interesting differential system. Many of you probably have houses that have thermostats. We have a thermostat here somewhere. Somewhere here is a thermostat. Right? What does a thermostat actually do? How does a thermostat work? Thermostat has to
turn on and off until it gets to the right temperature?
Yeah, so there's some temperature, you have a dial of some sort, if you're very fancy, you have like a Nest or something, right? And then like a thermostat is a device for stealing data about you, but let's pretend, let's ignore that for a moment. Okay, so along the way it might have the useful side effect of also adjusting the temperature in your house. So what is a thermostat? You have a thing that is called a set point. It's a term of art that control theorists like to use. It's a set point. And a set point is basically, that's the thing you are trying to reach. Okay? And what happens if you naively do this is, so here is my set point, right? So I set my temperature to be, I don't know, 65 or something like that, right? And right now the temperature is 60. Okay? So a natural strategy would be to say, well, let's see, am I below the temperature? Yes, I am. So what should I do? What are the outputs? You have basically three outputs. Turn up the heat, turn down the heat, turn up the heat, turn on the AC, and do nothing, right? Roughly speaking. Okay? So I'm below 65, so I should turn up the heat. Okay, so I turn up the heat, and now I go up to, I don't know, I go from 60 to 62. I'm still below 65, turn up the heat. Okay, I'm here, turn up the heat. I get here, but the problem is, I've been heating the place all along, so I overshoot. Well, I overshot, so now next time I sense the temperature, oh, it's too hot, I need to cool it down, turn on the AC, right? You can see what happens. So you get unstable behaviors, what are called unstable behaviors. You don't actually end up at the equilibrium that you're trying to reach. So people realize this, they actually realized this in an interesting context. The interesting context was, how do you turn a giant ship? Right? I mean, people talk about, oh, it's like turning an aircraft carrier. Well, because turning an aircraft carrier is really hard, right? You got to turn it a little bit, it doesn't do much. You turn it a little more, it doesn't do much. You finally give it a great big yank and wham! It's gone and destroyed like half your fleet or something, right? So it's the same instability problem, and that was the context in which people started studying this problem. So they said, okay, we need to figure out how much force to apply and when to apply the force. Okay? So they recognize that what you want is you want to apply the force, first of all, proportional to how far off you are. If you set 65 and it's 30 in your house, you probably want to really crank it up, right? There's no harm in cranking it up. But if it's 63, you don't want to turn your furnace on to full. Right? So you want to have something that is proportional to how far off you are. Yes?
But that causes oscillation.
Yeah, so we could spend like a semester roughly on this? Okay, so then you want to know something about the history of how much you have used. Okay? So you get an integral term. And finally, you want to look at where you are in the curve, like what is the derivative of where you are in your control. And that's called the differential term. So what you end up is something called a PID controller. Okay? Proportional integral differential controller. And there's a whole branch of mathematics called control theory that studies things like PID controllers and shows you how you can actually get to something that is stable and gets you to an equilibrium point instead of constantly bouncing up and down. Okay? And it turns out, like in actual hardware, you don't want to build a PID controller because I means an integral, which means you have history. And history is bad in hardware because it means memory, and you don't want to build memory into like cheap devices. So you tend to have PD controllers instead, and you can see what it, what is the like a typical math exercise is. What is the stability difference between PD controllers and PID controllers? Okay. But again, if you want to study the physics of a controller in high school, you don't, because there is no nice little function that says, oh, given this, produce that. You do it in differential form. So I'm going to guess most of your physics classes didn't really talk about PID controllers. Safe bet? Yeah. That's the interesting part of physics, actually. Okay. So I mean, just as an aside, this is we've been running a high school physics program for several years now, and this is what we do. We teach them differential forms and get them to do the fun physics instead. The trick, of course, is not the students, it's the teachers, because physics teachers who studied differential equations in college have been cultured to understand physics as the physics of closed forms. And so the trick is getting the teachers to understand that's not physics, and then once you do that, the students come along just fine. So PID controllers, lots of different systems end up having this differential form where you study the model, you talk about effects on the model, and it's just updates. Okay? And if you go to the applied math department, you can learn more about control theory. Okay? So I promised you that we would talk about infinities. So let me get back to that point to close out. Let me give you a sense of what systems look like. I mean, you're not here to take physics from me, thank goodness for you. But you are here to learn some computer science, I hope. So let me give you a sense of what computer systems look like. Real systems tend to look like the following. And I'm going to use a term here, reactive systems. Okay. Which describes your phone, your web browser, your GUIs, most of the things that you interact with, your thermostat, your, by the way, PID control also in your car, cruise control, same problem. You don't want to overshoot, you don't want to undershoot, you don't want to speed up too much and end up overshooting and then braking. Certainly, cruise control, by the way, is a little bit of a special case, right? Because in a PID control, in a household thermostat, there's no penalty for going above the set point. Yeah, this penalty is like red and blue lights in your rearview mirror. So it's a slightly different problem, which actually makes it a little mathematically interesting. So what you have, all of these are reactive systems. Okay, they get some stimulus from the world. The stimulus may be the current temperature. The stimulus may be the current speed of the car. The stimulus may be the current bearing of the aircraft carrier. The stimulus may be what button somebody pressed. Stimulus may be what is the current time on the clock. A tick just happened. So the world sends stimuli in. Okay? And systems have what is called an event loop. So time is going this way. You have an event loop. And so the event loop looks at the stimulus and says, I need to call something that can handle the stimulus. And in our framework, we've split it out so that you can see that clearly. If it's a tick, then it's going to call an on tick. If it's a key, it's going to call an on key. If it's a mouse, it's going to call an on mouse, whatever, right? So it's going to call something. And then something runs for a little while, does some computation, comes back with an answer, right? Which gets sent out to the world, like this is a to draw. Okay? And then in response to that, the world might decide to send you another event. And then you do something else, and you come back, and you go back, and so on. Okay? This is how most systems actually work. Industrial control systems, like, there is way, way, way more industrial computation going on than any of your desktop, tabletop, laptop, phone top computation, right? Tons and tons and tons of industrial systems out there. And they actually require you to understand this and understand that to build good industrial systems. They all have this basic high-level structure. Think about the consequence of what I just drew. The blue parts are your program. Your program doesn't get to just run and take over the world and decide everything that it wants to do. Your program is a slave to the world, right? It's just listening to the sounds of the universe and responding to the sounds of the universe. If the universe sends it a tick, it has to respond to a tick. If the universe presses a key, it has to respond to a key. The universe sends a network packet, it's got to respond to a network packet. Okay? Your program is this completely secondary entity. It doesn't even get to run properly. It runs for a little while, it has to stop. It runs for a little while, has to stop. Runs for a little while, has to stop. And moreover, it has to somehow resume computation. Right? It has to remember where it left off and continue from where it left off. Because if it forgot everything, then this code would just be, so imagine, let's think about what this would look like if it forgot everything, right? Let's imagine you were writing the code for, I don't know, like orbits or something, right? Some sort of aircraft reservation site. So somebody comes and says, I would like a flight from, I don't know, Providence to San Jose. Okay, great. It comes back and says, here's a list of options. And it prints out a list of options. Now they come back and say, I would like the first of those options, please. Okay? It comes in and says, first of what? That's what it would mean to have forgotten everything. Right? So somehow it has to remember what those options were. Say, first of all, you want that particular flight. Not a problem. I'll make a reservation for you. That's not trivial. So typically, you do this in somewhat complicated ways. What we have been doing in in reactors is to say you will return some state. And the event loop will remember the state for you and send it back to you. So your computation really can halt over here, but when it resumes, the information you needed to percolate is going to be in the world, in the state, the model. This actually ties to something else in computer science. When you build long-running systems that have to do something significant, you run into problems where pretty soon your computations take longer than the MTBF, mean time between failures. Computers die all the time. And when you run computers at the scale of, I don't know, Amazon or Google something, these statistical numbers become very real. There are always computers dying. So when you're running your computation, you have to assume that at some point your computer might just die. So you have to resume it. If it's a significant enough computation, you can't start from scratch. So when I used to do computational biology, we would have runs that literally ran for about 3 to 4 weeks. We'd get these huge data sets and run for 3 to 4 weeks. That was standard. Okay? You can't restart those. You don't want to restart 3 weeks in, start again. In fact, it's worse. We had, laptop machines were not very reliable back then, so you couldn't get a guarantee that you'd ever finish, even if you're willing to restart. So what you have to do is you have to checkpoint. You have to basically say, I can record the state of the system so reliably that when I come back up and read this checkpoint, it's as if the program had not stopped running. That's called checkpointing. It's a standard thing that you do when you build large systems. Checkpointing is basically nothing but figuring out what is the state of the system. The same identification process we went through. Imagine your Pong game got cut off and you had to resume your Pong game. You want it to look as if nothing had ever stopped. What do you need for that? You need all the varying parts. You don't need the constant parts. You don't need the background image stuff because it's constant. You need all the varying parts. What are the varying parts? That's the state. That's the model. Right? So what we've just done over the past few days ties to a whole bunch of different things. It ties to how we think about modeling physical systems in terms of differential systems rather than time parametric systems. It ties to understanding how reactive systems work. It ties to how we build real systems in terms of checkpoints, which is getting to the essence of things. All of these things now tie together. Right? And just keep in mind, real computations, you probably, it's like one of the things we say in computer science, right? Infinite loops are a bad thing, right? Infinite loops are obviously a bad thing, right? Obviously a bad thing. You wouldn't want to run a program with an infinite loop, would you? Of course not. None of you ever runs a program with an infinite loop.
Totally. That's not true.
Do you run a program with an infinite loop? Knowingly? Really? What program do you run with an infinite loop?
So like sometimes when you're using Java things.
Sometimes when you're using Java things. Games. How many of you like your operating system to shut down after a few hours? Your operating system had better be an infinite loop. When it's not, you tweet about it. Right? You get angry when your operating system terminates. You want your watch, you got a watch there. There's some code running on your watch. You want your watch to say, that's been long enough. It's an infinite loop. There's code running on those elevators there. Every time the elevators, exactly. Every time the elevators don't work, how pissed off do you get? Your networking, the routers that route your network packets, would you be okay with that saying, that's been long enough, I think I should shut. You get mad when infinite loops shut down. So all the interesting systems you run are infinite loops. Your cell phone operating system, everything's an infinite loop. Right? The world is full of infinite loops. And in fact, one of the challenges is to keep the infinite loop running for infinitely long. Okay? So that's what real reactive systems are. So Monday we talked about infinitely long data. Wednesday and Friday we've talked about infinitely long running programs. But the reality is they're not one monolithic thing. They're infinitely long running pieces of little pieces of computation. That's the essence of reactive systems. Okay?
and hopefully later in your Brown curriculum, you'll learn more about these things. Go have a great break. Enjoy yourselves. Get out. Have fun.